We are still continuing with modern physics of ordinary level or level, and this topic is usually taught in senior 3 or senior 4, but according to the NCDC syllabus it's supposed to be for senior 4. That's why it's labeled as for physics, modern physics, and this is part 2C. Part 2 has 3 subsections. There was part A, part 2A, part 2B, and part 2C now that we're going to look at. And this part deals with specifically this very interesting portion that we call half-life. Half-life as part of the nuclear process of radioactivity. So we're going to explore half-life. Pay close attention. I'm still your host, Monday Dennis Max Maths, and I request those people, or I actually remind the people who are just watching this maybe as their first video to go and visit the rest of the videos that I've uploaded on my YouTube channel. YouTube channel, it's labeled, it's named Monday Dennis Uganda. Monday Dennis Uganda. You'll access all the videos of physics that you need to excel with a distinction 1. Okay, now we want to look at half-life, which is denoted as T a half, small t and a half. Half-life is the time taken for a radioactive material to decay to half its original mass. We are defining half-life as the time taken for a radioactive material to decay. Where there is decay, you can say disintegrates, or you can say to decompose, but it is to decay to half its original mass. In terms of activity, half-life is the time taken for a radioactive material to decay to half its original activity. So we can now define even in terms of activity. We shall look at activity in details, but activity is defined as the number of disintegrations per second. Yeah, the number of disintegrations per second. The number of in simple terms, the number of radioactive atoms that are disintegrating or are decaying per second. That is what we call the activity. So we are saying in terms of activity, you can decide to define half-life as time taken for a radioactive material to decay to half its original activity. And activity is the number of disintegrations per second. It's measured in counts per second. Now, calculations involving half-life have basically 4 methods. Method 1 is what we call the chain method, a very cheap method. Actually, many students like using this one. All methods are easy. They are very easy, but this one is just so basic. If m0 is the original mass, or what we call the initial mass, of a radioactive material, and t is the time taken for the decay, then now t is the total time taken for the decay. m0 is the original mass of a radioactive material. Now you are starting with m0. If it decays to half, that is m0 over 2. You started with m0, now it has decayed to m0 over 2. The time taken, remember we said, for a radioactive material to decay to half, this m0 over 2 is half the original mass. That time is what we call half-life. Again, when that m0 over 2 decays to m0 over 4, because m0 over 4, yes, if you divide this by 2, you get m0 over 4. The time taken for it to decay is still another half-life. So, again, the time taken for m0 over 4 to decay to m0 over 8 is still another half-life. And again, the time taken for m0 over 8 to decay to m0 over 16. Because now, m0 over 8 divided by 2, half of this is m0 over 16. Still, that's another half-life. The process continues. I can't represent everything here. It continues almost indefinitely, but it continues until all radioactive atoms have decayed. Now, you realize that here there are 4 half-lives. This is the first one, the second one, the third one, and the fourth. So these 4 half-lives here are giving us the total time. They are giving us the total time. We said T is the total time taken for the decay. Then this is true. According to what I've represented here, we are having 4 decays. The number of decays is the first decay here, another decay, another decay, another decay. So there are 4 decays. The number of decays is 4. So we're saying 4 half-lives is equal to T. Now the decays we are talking about, they are the decays from a certain mass to half that mass. So generally, we quote this as N, the number of decays times T1/2 is equal to T. Please don't forget this formula here. We shall need this simple equation here. It's not a formula, but just an equation. Very easy to remember. NT1/2 is equal to T. NT1/2 is equal to T. Or, on the other hand, you can choose to write also that N alone is equal to T over T1/2. You see that? From here, this is true. This is very true. Very true. Please observe that if you make N the subject, you end up with N is equal to T over T1/2. Let's proceed. Now, the second method, which is, I don't know whether this is cheaper. Some people told me that this method is cheaper than the one that most students like. Yeah, you know, one man's meat is another man's poison. Someone said one man's meat complete, and the other said another man ate it. So method 2, which is the table method. We have our table. We shall have 2 columns. In the first column, we are putting the time taken for the decay, and then the mass remaining. Please note this mass remaining, not just mass, but the mass remaining. Initial time is 0. That means when time is 0, you have the original mass, m0. Let's again create some more pair of data. After a half-life, that is T1/2, after this time, T1/2, which is the half-life, this mass, the remaining mass will be m0 over 2. After, again, another half-life, that means now these are 2 half-lives. The first one, the second, so we keep adding half-lives. Where there is time taken, you keep adding the half-life. And where there is the remaining mass, you keep dividing by 2. Have you really grasped that? I said, where there is time taken, you keep dividing, you keep adding a half-life. Here it was 0, we added 1 half-life, go to your half. We added another one, now there are 2. But this side you keep dividing by 2. Therefore here it's going to be m0 over 4. Then we add another half-life to the time taken. They become 3 half-lives. The mass remaining will be, keep dividing by 2. It will be m0 over 8. And then again we add another half-life to the side of the time taken. They become 4 half-lives. The mass remaining now will be m0 over 16. Now we have a third method, which is the formula method. You just write a few formulae. The formulae that we use are very easy, and they always depend on what has been given. They can give you the mass, they can give you the activity, they can give you percentage, they can give you the number of radioactive atoms. So whatever they give you, just quote. Now, this formula is very easy to remember. M is equal to m0 times a half power n. Remember, what was our n? We talked about it. Our n, we talked about it. Remember, we talked about it. Come on. Somewhere, I remember. Yes, here we said the n is equal to T over T1/2. Don't forget that, please. Please don't forget it. Now, here we are saying that in the formula method, it is the mass remaining is equal to original mass times a half power n. But what is n? N is equal to T over T a half. On the other hand, you can decide to quote in terms of activity, where activity remaining is equal to original activity times a half power n. Or in terms of the number of radioactive atoms present, you can say n is equal to n naught times a half power n. And you can also, they can give in terms of percentage, where you say p is equal to p naught times a half power n, where n is equal to t over t a half. Okay. From this formula, you remember that we quoted, you get n is equal to t over t a half. Now, where m naught is the original mass, m is the mass remaining after time t, n is the number of decays or integrations in time t, this n. N naught is the original activity, a is the activity remaining after time t, and the activity after time t, and n is the number of radioactive atoms in a material. Now, they may ask you, instead of asking for the mass remaining, they ask for the mass which has decayed. I think this is logic. Just logic. The mass which has decayed, or the mass decayed after time t, is always given by original mass minus the remaining mass. So original mass minus the remaining mass. This m stands for the mass remaining. M naught is the original mass. So to get the mass which has decayed, just subtract what was originally there minus what is present. So examples. Now I want you to pay close attention. Number 1, a radioactive material has a half-life of 5 hours. If the initial mass of the material is 8 grams, part A, determine the mass that remains after 15 hours. And part B, what mass decays in this time. Now, we are going to do this together. I want you to follow me closely. I will try to employ all the methods that we've talked about, so please pay close attention. Let me start with the first method, the chain method. We are given that originally we have 8 grams. So you write 8.0 grams originally. Will decay to, what is a half of 8? That is 4. So we write 4.0 grams. Now they said a radioactive material has a half-life of 5 hours. That means it has taken 5 hours. It takes 5 hours for 8 grams to decay to 4 grams. Now they said determine the mass that remains after 15 hours. Now so far we have 5 hours. So let's continue with the decay. The 4 grams now will decay to 2.0 grams. So still the time taken is 5 hours. You keep dividing this mass, keep dividing the mass by 2. 8 divided by 2, 8.0 divided by 2 get 4.0. 4.0 divided by 2 you get 2.0. And this one also, when it decays, 2.0 divided by 2 you get 1.0 grams. So you see, we have 1.0 grams and still the time taken is 5 hours. Now, we have made our 15 hours. 5 plus 5 plus 5. That is our 15 hours. And the question says, determine the mass that remains after 15 hours. So, our part A here, mass remaining, the mass remaining after 15 hours. 15 hours is 1.0 grams. Oh, I don't have a stylus. Sorry. Oh, it just rubbed everything. Sorry about that. I think it's just an opportunity for me to repeat for whoever maybe had not picked it up properly. But let me do it again. We said we started with 8 grams, 8.0 grams, decaying to 4.0 grams, and the time taken for this mass to decay to have its original mass is the half-life, which is 5 hours. Then also 4.0 will decay to 2.0 grams after 5 hours, and also this 2.0 will decay to 1.0 grams after 5 hours. Now the question was, determine the mass that remains after 15 hours. I've already told you that here we only stop after, like here they asked for the 15 hours. Realize that 5 plus 5 plus 5 will give us a 15 hours. Therefore, for part A, we are answering and saying the mass that remains, mass remaining after 15 hours is 1.0 grams. Okay, this time it accepted. Part B says what mass decays in this time. So mass decayed mass, remember we said, is equal to original mass, is equal to the original mass m0 minus the mass which is remaining. What was our original mass? It was 8 grams. So minus the mass remaining, which is 1.0 grams. So from which we realize that the mass which has decayed now is 7.0 grams in this time. Okay. Let's now try to employ another method, which is the table method. We try to use the table. If you use a table, what do you end up with? For the table method or the tabular method, the approach is very easy. All you do is you draw a table and you put to the right you put time taken. We are putting time taken, and then to the left you put time taken, and to the right you put mass remaining. Okay, please, you will excuse my writing. I'm just using a free hand because I don't have a stylus here. We are drawing a table. Hope everyone will be able to see properly. Now, initially, at time 0, at the beginning, the mass was 8.0 grams. This is 0 hours. Then, after every 5 hours, because the half-life is 5, after every 5 hours, the mass now, the remaining mass will be half. So that means we shall have 4.0 grams. After now 10 hours, this will be half of 4, which is 2.0 grams. Then after now the 15 hours, you'll have 1.0 grams. Let's close our table. Oh, I drew a bigger one. Okay. So the question was, what mass remains after 15 hours? You see, after 15 hours, the remaining mass is this one, 1.0 grams. So if they ask for the mass decayed, the mass decayed is just the 8, the way we did it, minus this one here. Please, you make that, you write in words down. I will not write here because I've used up almost all the space. Now, let's also try the last method, which is the third method. I will not talk about the other method of the graphical method because for it requires data. The third method is that of the formula. Remember, the original mass, we are given the original mass as 8 grams. And then we are told the half-life T1/2 is 5 hours. And then the total time was 15 hours. So always, to make life easy, first get the value of n. N is equal to T over T1/2, which will be equal to, what is our T? The total time is 5 hours, divided by the half-life, which is 15 hours, sorry, for the time taken was T, which is 15 hours, and then the half-life is 5 hours. I had interchanged. So you end up with n, which is the number of integrations as 3, number of disintegrations or number of decays as 3. Okay? N is equal to 3. Now let's go back to our formula, if you remember very well. We said if you use the formula is m mass remaining is equal to m0 times 1/2 power n. 1/2 power n. So the mass remaining will be equal to, what was the original mass? We had the 8 times 1/2 power 3, which becomes 8 times 1 power 3 is 1, 2 power 3 is 8. So you end up with 1 gram. Therefore, still just like in the previous methods, we realize that the mass remaining after 15 hours is 1.0 grams. And here, if you go ahead, please, this was not a Z, this is an equal sign. If you go ahead and get the mass which has decayed, mass decayed is equal to the original mass minus the mass remaining, which will still give you that 7. I have now showed you how to use all the 3 methods for that example. I want us to proceed and look at now number 2. A radioactive material has a half-life of 4 hours. If the initial mass is 9.6, calculate the mass remaining after 24 hours. Part B, the mass that decayed after the 24 hours. I think here I'm just going to employ only one formula, only one. Let me use the chain method here. You can also pause and do. Yes, you can pause and do, and then you compare afterwards with the answer I will have obtained. They're saying a radioactive material has a half-life of 4 hours. So our half-life is 4 hours. The initial mass is 9.6 grams. So let's start from 9.6 grams. Now, after every 4 hours, because the half-life is 4 hours, after every 4 hours, the mass will be half of what was there. So we are starting from 9.6. If you press on the calculator, you may even just do without a calculator. 9.6 divided by 2, you get 4.8 grams. The time taken from 9.6 grams to decay to 4.8 is the half-life of that material, which is 4 hours. Let's continue. This also will decay to 2.4 grams, because that is half. 4.8 divided by 2 get 2.4. And still the time taken, the half-life, you just keep putting the same, 4 hours. Then this also decays to 2.4 divided by 2, you get what? You get 1.2 grams. This is 4 hours. Now they said calculate the mass remaining after 24 hours. Now you see how many hours we have taken. 4 plus 4 that is 8 plus 4 is 12. We still have a long way to go. Okay, let the decay continue. So 1.2 divide by 2, what do you get? You get 0.6 grams. Still the time taken is 4 hours. You see that? So far, how many hours do we have? Those are 16. Let's continue. 0.6 divide by 2, you get 0.3 grams. The time taken here is still 4 hours. So we so far have 4 plus 4 plus 4 plus 4 plus 4, that's 20 hours. Let the decay continue. What is half of 0.3? That is 0.15 grams. So still here 4 hours. Now the question was, calculate the mass remaining after 24 hours. So what's the mass remaining after 24 hours? Mass remaining after 24 hours. So we are going to say for part A, mass remaining after 24 hours. After 24 hours is, we got 0.15 grams. Full stop. Part B said, what is the mass that has decayed? What mass will have decayed? Mass decayed, remember our formula. Mass decayed is equal to original mass minus the mass remaining, which is going to be, the original mass was 9 point what? 0.6. Okay, minus, what is the mass remaining? 0.15. And what do you end up with when you press on your calculator? 9.6 minus 0.15, you end up with 9.45. I'm just taking it slowly so that everyone can participate. I know you have your calculator with you. So the mass decayed is equal to 9.45 grams. That easy. Okay. Oh, I wrote in some space of some work. Let me rub this away. Sorry about that. Just need to remove this. Number 3, a radioactive material has a half-life of 4 years. The initial mass of the material is 16.8 grams. Find, part A, the mass remaining after 16 years. Part B, the time taken for the material to decay to 2.1 grams. 2.1 grams. For this case, actually, let me use another method. Don't know which one you prefer, but for me, let me just use the okay, let's use the formula. First of all, let's use the formula. They are saying a radioactive material has a half-life of 4 years. So T1/2, you denote, and so T1/2, you write down, is equal to 4 years. Okay. The initial mass of the material is 16. So initial mass is 16.8 grams. they are asking for the time, for the mass remaining after 16 years. So the time they are giving us is 16 years. So get your half-life. Half-life is 4 years already. Sorry, you don't need to get it, it's already given. Now the first step always when they've given you total time and half-life is to get the number of decays. So let's start by getting the number of decays. N is equal to T divided by T a half, divided by T a half, which is going to be 16 over 4, giving us 4. Good. Now, part A asked us to get the remaining mass after 16 years. So we are going to use, for our part A, we are going to use the formula. A mass remaining is equal to original mass times, times a half power, this is not clear, okay, we said it's M is equal to M naught times a half power N. So what was M naught? We are having 16.8 times a half power 4, which will be 16.8 times 1 power 4 is 1, 2 power 4 is 16. And what do you end up with? What does the calculator give you? Please press your calculator, pull it out and press it. 16.8 divided by 16. We are getting 1.05 grams. Exactly. So the mass remaining after 16 years is 1.005 grams. 1.05 grams. Now part B says, what's the time taken for the material to decay to 2.1 grams? Now here they have given you the remaining mass. So we are just going to use the same approach. We are still maintaining the formula method. I think maybe I will also look at another method, and then you see which one is easier and more convenient for you. We are doing part B. Part B, which requires us to get the time taken for the remaining mass to be 2.1 grams. Now, if they have given us the remaining mass, so we have to use the formula. Remember, with the formula, remaining mass is equal to original mass times a half, and then you raise to power n. So the mass that is remaining is 2.1. The original mass is 16.8 times a half power n. Now you're going to get n, which is the number of decays. So we can decide here to divide both sides by 16.8, even this way by 16.8. Now this will cancel with that, and then you'll have a half power n equals to 2.1. If you get 2.1, you can use this you can handle that using logarithms. Those of you that are well acquainted with mathematics, this is just very easy. So we are ending up with 0.125. Now in index form, 0.125 for your own information is the same as 125 over 1000. To simplify life for some people, is equal to a half power n. And then when you keep dividing this, what do you end up with? If you divide that in the simplest and the lowest, in that fraction in its simplest terms, you end up with 1 over 8. You see that is equal to a half power n, from which you can say 1 over 8 is equal to 1 power n is 1 over 2 power n. So this is a 1, also this is a 1. So 8 is equal to power n. You can actually now handle this 8 and write it as 2 power 3 is equal to 1 over 2 power n. So if you make a comparison, you realize that your n is equal to 3. Sorry about this. N implying that our n is equal to 3. And once you know the value of n, use now the formula that we had. You remember our formula? We said that t, the time taken, is equal to n times t a half, which is going to be 3 times what's your half-life? What was our half-life? 4. Yes, it was 4 years. So we end up with 12 years. Yes. So the time taken for it to decay to 2.1 grams is 12 years using the formula. Now someone may say, can't we do it in a cheaper way? Yes, we can. We can. And actually, when it comes to such numbers, I always encourage students to use the table, because the table is always very straightforward. Very, very straightforward. Let's go back to our question. The question said a radioactive material has a half-life of 4 years. The initial mass of the material is 16.8. Okay. Now we are going to do just one table, which will cater for part A and part B if you are using the table method. Look at this. Sorry, didn't want a highlighter, want a pen. For the table, we put here the time taken, and then this other side we put the mass remaining. Your table has to be very smart, eh? Make sure you use a ruler. Don't draw with free hands like me. Okay. The original mass was 16.8 grams. Was it 16.8? Yes, I think it was 16.8. So, initially, the time is 0. Now, after the half-life is 4 years. So, after every 4 years, this will be half. What is the half of 16.8? 16.8 divided by 2, you get 8.4 grams. After more 4 years, remember we said with this table method, where there is a time taken, you keep adding the half-life. For the mass remaining, you keep dividing by 2. So let's add here more 4 years, you come to 8 years. So after 8 years, you'll have 8.4 divided by 2 is 4.2 grams. Let's continue. So we add another half-life, which is, now when you add if you add the 4 to this 8, you get 12 after 12 years. Still we divide 4.2 by 2, you get 2.1 grams. We add more. If you add 12 plus 4, you get 16 years. The question said mass remaining after 16 years. So 16 years. Divide this by 2, you get 1.05 grams. So you see with the table here, we have both parts answered. Part A said, without even hassling, Part A said, what is the mass remaining after 16 years? So you say mass remaining, the mass remaining after 16 years, after 16 years is, what did we get? We got 1.05 grams. If they ask for the mass decayed, you know what to do. You subtract the 16.8 minus the 1.05 grams. Part B said, the time taken for the material to decay to for the remaining mass to be 2.1 grams. You see, here you just read it directly. So the time taken for the material to decay to 2.1 grams is 12 years. Yeah, there is even no need for you to bother yourself. So the time for part B I will not write, but the time taken for it to decay to 2.1 is directly 12 years. Okay, now let's look at number 4, which says a radioactive substance decays to 1/16 of its original mass after 16 days. What is the half-life of the radioactive material? Part B, what fraction of the original material will have decayed after 20 days? The fraction which will have decayed after 20 days. I want to use the method that students usually find more convenient when it comes to every question, that is the table method, and even the chain method also, but I will use the table. Now, a radioactive substance, they said it decays to 1/16 of its original mass after 16 days. So we are going to draw our table. Remember, with our table, we write here the time taken, and then this other side we write the mass remaining. Okay. The time taken, initially we start from 0, and the mass remaining, let us use the original mass as m0. Okay, because they have not given it to us, just use m0. Now we are going to go until we keep putting the decays until we get m0/16, because it's saying a radioactive material substance decays to 1/16 of its original mass. That means we will have to put the decays, we show the decays until we have 1/16 of m0, which is m0/16. Now let's go. So here we will have, after 1 half-life, which is you put to t1/2, this one will become m0/2. Then after now 2 half-lives, after 2 half-lives, you're going to have m0, come on, over 4. Okay, after the third half-life, we are having m0/8. After the fourth half-life, so you have m0/16. Or you can simply just keep quoting them differently by putting, so you keep putting, you can say this is a half m0. This can also be written as a quarter m0. This can be written as 1/8 m0, and this can also be written as 1/16 of the original mass. So the question says The statement says a radioactive substance decays to 1/16 of its original mass after 16 days. Now do you see? The time taken here, according to our formula, our method, we're having 4 half-lives. And they're telling us that it's after 16 days. You see that? That means that this should be equivalent to the 16 days. You see that? Therefore, part A, which says what is the half-life of the radioactive material, can easily be obtained by equating, because they told us that it's decaying to 1/16 after 16 days. So it means that 4 T a half. Oh my God. So I'm saying 4 T a half. Do you know where I'm getting that from? I'm getting it from here. The total time taken, because according to the statement, they told us that it is taking 16 days. So that means our T a half is equal to 16/4 is 4 days. So the half-life is 4 days. Now part B says what fraction will have decayed after 20 days? After 20 days. Now, if you're using this table, the table method, you just proceed downwards, just because I don't have space. When you proceed and add another half-life so that they become 5, or in simple terms, now that you know the half-life, just add it to the 16, add more, 4 days, you end up with the 20. So the fraction which will be remaining will be 1/32. 1/32 m0. See that? Part B said what fraction of the original mass will have decayed? Now this is the remaining fraction. So part B, fraction which has decayed, the decayed fraction will be the decayed fraction, or the fraction of the decayed mass is going to be the whole number which you started with minus 1/32, which is definitely going to give you 31/32. That is the mass, the fraction of the original mass, which will have decayed after the 20 days. You can now decide, you can even do this number using the other methods, no problem. Let me look at, I think, the third last example. A radioactive nucleus has a half-life of 5,600 years. Determine the time taken for 96.875% of its mass to decay. Part B, find a fraction of the original mass that remains after 22400 years. You see? This is also just very easy. I know you can do it. I don't know which method we should. Okay, you can use any. But I want you to bear in mind that here they are saying that they're asking you to determine the time taken for this to decay 96.875. And for half-life, we always deal with the remaining mass, remaining activity, remaining number of radioactive atoms, remaining percentage. But here they have given us the decayed percentage. So one thing you have to realize is that you say percentage remaining here. Percentage remaining is, we are going to say remaining percentage, your percentage remaining is 100, which was the original, minus 96.875%. And what does that give us? 0.125%. See that? Yes, so that means you have to look at these integrations or the decays until you remain with this percentage. So you can use any of the three methods, they will all work. Actually, let me use the chain because of the space. For Roman 1, look at this. This time we're not dealing with the masses, we are going to deal with the percentage. You start with 100%. After one half-life, which is 5,600 years, we shall have 50%, because the percentage will be divided. Then after another half-life, which is 5,600 years, we shall have 25%. After another half-life, which is 5,600 years, we shall have 12.5%, not grams, I almost wrote grams, percent. Still, after another 5,600 years, what is 12.5 divided by 2? We shall have 6.25. 6.25%. After another half-life, we shall remain with 3.125%. Exactly. So determine the time taken for 96.875% of its mass to decay. So the total time taken here is going to be 5. Remember the time taken. I want you to remember this. I just want to change the color here. Remember that the time taken is equal to number of decays times the half-life. So how many decays are here? We have the first one, the second, the third, the fourth, and the fifth. So we are just going to get 5 times 5,600. And what does the calculator give you? When you get 5600 times 5, you get 28,000 years. That means the time taken for this 96.875% of its mass to decay is 28000 years. Roman 2 says find a fraction of its original mass that remains after 22400 years. Now, can we try to add? Look at this. 5600, 5600. If the time is 22400, how many decays will those be? Let's try to divide to answer part B. Let's get 22400 divide by 5600. You get 4 decays. That means this plus that plus this one plus this one plus this one plus this one. Only 4 decays. 4 decays. Because when you divide 22400, divide by the half-life, which is 5600, you end up with only 4 decays. Therefore, Roman 2 says find a fraction of its original mass that remains after 22400 years. The fraction remaining will be this. So write this in fraction. 6.25% is 6.25. To answer part 2, you're having 6.25%, which you can write as 6.25 over 100, and you simplify that further, I don't know what you're going to end up with. You can just finish that. Yes. So let's try to use the table. If you're using the table, this side we put the time. Oh, will this space be enough for us? Let me just put it on a new page. So we are using the table. We shall put time taken here, and then this other side we are putting remaining percentage or percentage remaining, not mass remaining, but this time a reason in terms of percentage. So initially we shall have 100%. Then after, remember our question here is asking us to get, they gave us the half-life. Yes, they gave us the half-life. Okay. That means after every 5,000, sorry, where were we? After every 5,600 years. So this will be half of 100 is 50. So let's add 5,600. If you add the 5,600, what do you get? 11,200. We shall have 25%. These are percentages. Percent. Then here we keep adding. If you add another half-life plus 5,600, you get 16,800 years, and this will be 12.5%. Because for the percentage remaining, just like we were doing for the mass, just keep dividing by 2, while for the half-life, the time taken, we keep adding the half-life. So here again we add another half-life plus 5600, you end up with 22400. This is 6.25%. And then when you add plus we're adding plus 5600, we have 28, we are having 3.125%. This has to be a table. Please enclose it properly. Don't draw like mine, draw a smart one using a pen. Sorry. Okay, there we are. You draw properly. And so part A required us to determine the time. You see, the time is just direct here. 28000 years direct. And then what time is it taken for sorry, the question was a percentage remaining after this time. You see, for the table you just read everything directly. I'll not explain any further because I'm making the video very long. Let me jump into other things now. Part 6, number 6 says 87.5% of a radioactive material decays after 60 years. What is a half-life? I won't explain that, I promise. Number 7, the activity of a radioactive substance decomposes from 4,000 counts per minute to 250 counts per minute in 40 minutes. What is the half-life? of the substance. I think this is another thing which is very easy. Now here, instead of giving us the masses they are giving us the activity. I told you last time that they can give you activity, they can give you mass, or they can give you the number of radioactive atoms present. So here, what are we going to do? Let's use the chain method. The activity of a radioactive substance decomposes from 4,000. So we are starting with 4,000 counts per minute. So after one half-life, which is after t1/2, it will become a half. 4,000 divided by 2, you get 2,000. After another half-life, which is just another half-life, because they told us it decomposes to 25, so we just keep dividing by 2 until we get 2500. 25, not 2500. So after another half-life, we get 1,000. I'm putting grams. This is not true. Sorry, I made a mistake. This was supposed to be there. We are saying the activity, which is in counts per minute, not grams. Sorry about that, please. Okay. Now you see, after again another half-life, half of that of 1,000 is 5,000. Is 5,000 counts per minute. After another half-life, t1/2. After t1/2, you get to 50 counts per minute. So the statement says the activity of a radioactive substance decomposes from 4,000 counts per minute to 250 counts per minute in 40 minutes. What is the half-life of the substance? So how many decays do we have here? 1, 2, 3, 4. So you'll say that 4 half-lives give you, the total time they gave you was 40 minutes. You see how easy this becomes? So t1/2 is equal to 10 minutes. 10 minutes. Yeah. Please pardon my disorganization. I'm just trying to use available space. That is the half-life of the substance. Oh, thank God. After the 7th number, it's my turn to rest, just like God rested on the 7th day. Okay. So this is the exercise for you. I'm very excited to present it. Number 1, what happens to the activity of a radioactive material when Roman 1, its mass is increased? Remember, we said the activity is the number of disintegrations per second. So when you increase the mass, what will happen? I think I should throw some light here. The activity of a radioactive material actually will increase because you have increased the number of atoms. So the number of disintegrations per second will increase. Roman 2, what will happen to the temperature, to the activity, of a radioactive material when the temperature is increased? Let me say it again. What happens to the activity of a radioactive material when the temperature is increased? Now remember, we said the radioactivity is a spontaneous process. That means it happens without external influence. Whether you change the pressure or you change the temperature, it is not affected by temperature. Therefore, the activity neither increases nor decreases. It just remains the same, or is not affected. Number 2, I'm not going to read for you. Yeah. Number 3, right there. Actually, let me give you the whole page. You pause and do those questions and you submit, please. You submit. Thank you. Oh, the last method, the graphical method of determining half-life. This one is very easy. If you know how to plot graphs in practicals, you're safe. If you don't know how to plot, I should say there are two things involved. You either this one is supposed to be determining, sorry, there's an E missing here. The graphical method of determining half-life. Now, you either learn how to plot or you find this funny. So this is what we do. A radioactive material, this is what we do actually. If they ask you to describe, this is what you do. A radioactive material whose half-life is required is weighed and its initial mass m0 is recorded. As time increases, the remaining mass m of the material is recorded after regular time intervals, which you call t. So the results of t, the time taken, and m, which will be the remaining mass, are put in a suitable table. A graph of the remaining mass against the time is plotted. The time corresponding to half of the original mass, which is m0/2, gives the half-life, as simple as that. Also, the time interval between the time which corresponds to any mass, you can just use any mass, and the time that corresponds to half that mass is also the half-life. If this statement is confusing, please just stop here. Don't worry, but it's just also understandable. A graph of m against t for a radioactive decay. We will have a vertical line and a horizontal. On the vertical we're putting m in grams, on the horizontal we're putting t in seconds, and ensure that the vertical and the horizontal values start from 0, and then we plot a dot and a circle, dot and a circle, a dot and a circle, and then you draw a smooth curve through them, through the plotted points. Now the original mass is m0. Locate half of m0. Locate half of m0. So if this is 100, this will be 50. If this is 1000, this m0/2 will be at 500. So you just get m0, you look at the original mass, then where the half is. So locate it on the horizontal. Sorry, locate it and draw a horizontal line. Locate where m0/2 is and draw a horizontal line to touch your curve, and then draw a vertical one to connect here so that you can read the half-life. It's that easy, very, very easy. You can go ahead and use another mass, maybe around here, and you also you use another mass, determine half of it, which may be around here, and you also read another half-life so that you can have many and you get the average. Note, a similar graph is obtained for the number n of radioactive atoms against time, and also for the activity A against time. Now, a question. This question, please get a graph paper, or you can do it in a graph book and answer it. When a suitable counter was placed near a radioactive source, the following rates of emission were obtained at the times shown below. So we have this table, and the question says plot a graph, and using a graph paper or use it in a graph book. Plot a graph and use it to find the half-life of the source. This has been a very long video. Thank you for your patience, and I request you to proceed now to part 3, where we're going to look at cathode rays. We are saying S4 physics, modern physics already continued, and this time we are going to look at the cathode rays. I am so grateful to all of you people who are following me and who are making sure that you learn every day something new. I know you're going to excel. I'll be very happy to know that you scored, to know when you have scored a D1 in physics because of these videos that you are watching even during this time of the quarantine. And I am still your host, Mandy Dennis, Max Mas. I'm so glad that you've been following up to this point. Please don't give up, because winners never quit and quitters never win. And I encourage you please to check out my YouTube channel. It's Mandy Dennis Uganda. For more videos, please I encourage you, go to that channel and you'll find very many resources to help you. I'm still uploading, so therefore subscribe to the channel. May God bless you. Bye bye.